So this lecture we begin by looking at systems of parameters, and then we will prove the Krull's theorem about relating three things: dimension of a module, delta m, which is a polynomial, which is a degree of a Hilbert-Samuel polynomial, and S of m, which is the length of a system of parameters. Okay, so proposition. So throughout, again in this whole lecture, Rm is noetherian and m is finitely generated, R module, and we will not explicitly state this all the time, except maybe when we state the theorem. So another proposition, Sm, which is the minimum number S such that there exists some x1 through xs, so that m mod xm is m mod xs times m is a finite length, so called a system of parameters for m is greater than or equal to delta of m, which is a degree of a Hilbert-Samuel polynomial for any ideal m primary ideal I, irrespective of the ideal. So we can construct S of m, we can determine delta of m by looking at PIM for any I. So we will try to use something that is convenient for us. Okay. So let x1 through xs in m be such that m mod x, so I will just put underline to denote all the x's together, times m has finite length. The length of this module is finite. Okay. So it's enough to show that. So we want to show that delta m is less than or equal to s. Okay. If this is the case, then the minimum of all such possible also will be greater than or equal to this, if this is true for every s. Okay. So this is what we want to show. Okay. So we would like to choose some convenient I, construct with respect to a generating set for that I, and then conclude this. Okay, so let I be equal to the annihilator of m plus the ideal generated by these x's. Okay, and it will be an exercise to check that this I is m primary. In fact, a sequence like this will have this property if and only if annihilator m plus that ideal generated by that sequence is m primary. Okay, so exercise. The radical of I is m. Okay, so we can try to determine we can try to determine delta m by looking at PIM for this I. Okay. So how would we do this? We first have to write the associated graded ring as a quotient of a polynomial ring, associated graded ring for I. So we need to write the associated graded ring of R as a quotient of a finitely generated polynomial ring, okay, and then m is finitely generated over it. I mean, that's sorry, not the associated graded ring, associated graded module of m is finitely generated over it. And then we will use the property about the Hilbert function of such a module. Okay. So in order to write this, we have to make a choice of generators of m. So we'll choose the following. So let x1, keep the x1 through xs, and then we choose y s plus 1 through yt, okay, these, okay, from the annihilator. Remember, it is annihilator by plus x, so take the x's and generators for, this need not be a minimal generating set for I, but that is okay, just need to take some generating set, be a generating set of I. Okay, it need not be minimal, but that is fine. Okay, so now we can get the associated graded ring of R as a quotient of R mod I adjoint these many variables x1 through xs and capital Y s plus 1 through y s plus 1 through capital T. Okay. And what is the map? The map is the variable xi goes to the element the xi mod I square. So this is the degree 1 part of. Okay, so recall this is, remember, this is in degree 1 of the associated graded ring. Okay, and yi similarly goes to yi again mod I square. Okay, so we get a polynomial ring, and the associated graded module is a module over this. Okay, so therefore, okay, is annihilated by ys plus 1 through yt, because if you take an element in this, it is the residue class of some element of the module on which capital Yi acts as yi bar, and what is the multiplication? Yi bar times some m bar, where m is an element inside here, m is just yi times m bar, but yi times m is 0. So these elements are annihilated by this. Okay. Therefore, is a finitely generated graded module over the quotient ring. So this polynomial ring modulo the y's, because they anyway kill, over R mod I adjoint with sx variables and remaining ys plus 1 through yt, remaining y variables killed in s plus 1 through yt are killed. But this is also a polynomial ring. Recall that this is also a polynomial ring in x1 through xs. So associated graded ring is a finitely generated module over this ring. Okay. That's the observation. Okay. Of course, we cannot change this to xs. Here we are using I. It is just we only need the generators of the generators corresponding to the system of parameters and not for the annihilator. Okay. That's the observation that we want to make. Okay. And so what then this one says that the Hilbert polynomial of the associated graded ring of M has degree at most s minus 1. Okay. Therefore, the Hilbert-Samuel polynomial of M has degree with respect to I has degree at most s. This now implies that delta of M is less than or equal to s. Okay, so this is the okay. So in Krull's theorem, this is one step, but we will we want to look at some quick examples in Macaulay before we prove the theorem, Krull's theorem. Okay, so now let's look at this example. So the first example, so we have seen variations, I mean these ideals earlier. So in the input, we take some field adjoint two variables and we look at the ideal generated by x squared and xy. Okay. What we want to consider is the quotient, but the module is the quotient ring, but it's a little difficult. See, some of these functions are not defined for quotient rings. They're defined for ideals and modules. So it's a little, each time we construct a quotient ring, we have to tell Macaulay to convert it to a module, etc. These are just changing their types. So instead of worrying about all of these things, we will just worry about the minimal prime, just work directly in R. Okay. It's equivalent anyway. So we ask for minimal primes of x. We have computed this earlier. Any prime must contain x because of x squared, and x itself is a prime ideal in R, so it's a prime ideal in the quotient, and therefore it's a minimal prime. It is the minimal prime. Okay, we are searching for a way to find systems of parameters. Okay, or what would be a system of parameters for M. Okay, so we'll ask. Let's try x1. So we have to do some x1 through x's. So let's try x. Let's start with x1 equals x. Okay, so we ask R mod I plus ideal x. Okay, so this doesn't. Yeah, this is not. It didn't minimize the generators. We just give that way. So here I just ask. So it hasn't found minimal generators. So I ask to find the minimal generators of I plus ideal x and then construct the ideal from that. Yeah. So then if we ask that, this is the output. It says output is R mod x, which is what we expected. So if we chose x1 equals x, then we will need to choose some other x2, for example y, okay, because R mod x is isomorphic to k adjoint y. So we need to use something so that the quotient is a finite length module. Okay, I mean, ky is not a finite length R module. So so we have to choose two things if we started this way, at least two things, in fact only two things. But on the other hand, if we choose x1 to be y, okay, so let's check that thing. So we ask the same thing, I just add the ideal, take min-gens and then construct the ideal. So we would get y comma x squared as we, yeah, so we got one element. So therefore this is S of m in this case, m being R mod I is at most 1. But on the other hand, R mod I itself is not of finite length, because we know that if this has finite length, then it would be a finite dimensional vector space. But in this case, every power of y remains in the quotient, so it's not a finite length. So we need to go modulo at least one element, and in this case we have found one element, so we are done. So that says S of R equals 1. Okay. Now let's ask, why did choosing x1 fail? So the reason why it failed is x1 belongs to a minimal prime, that is x. Why did choosing x1 as x fail? Not just choosing x1. Why did choosing x1 equals x fail? So that's because that choice of x1 belongs to a minimal prime, which determines dimension of R mod I. In other words, from this minimal prime to a maximal ideal, there is one of maximum length. Okay, that is, you start with x and then go to x comma y. Okay, so there is one. Okay, so there is a chain of primes that starts at x and then attains the suprema of lengths of chains of primes. Okay. So therefore, that's the reason why this failed. Yeah. So one thing to note at this point is, we did this for the polynomial ring, but we chose elements inside the maximal ideal x comma y all throughout, so that if you just localized at the maximal ideal x comma y, we would have gotten the same conclusion. Okay. And there is this going back and forth between local rings like this, okay, and graded rings, which we will explore after we prove these results. Okay, and that's crucial to build some intuition about various things. So we will see. We'll have a couple of lectures on doing that thing, and all the more so because Macaulay 2 is, or any computational algebra system is very, is more adept at handling a graded situation than handling an arbitrary ring. Okay, so therefore we will do this translation between graded case and local case on and off, okay, and we will go over it in detail later. Okay, so, okay, but in this particular case, it's easy to see that if I had done the same calculations over the local ring, we would have got the same result. Now I join three variables and take the ideal xy comma xz. Okay, this is its minimal primes are y comma z and x, singleton x. That's so this one says x must, this the first generator says x must be in it or y must be in it. Second one says x must be in it or z must be in it. Therefore, if x is not there in a minimal prime, in any prime, then yz must be there. So that's the only minimal prime. Okay. So we already observed that there is no point picking elements inside a minimal prime that determines dimension. Okay. So here there are two minimal primes. Here there are two minimal primes. Here there are two minimal primes. One from this minimal prime x, there is a chain of length at least 2, which is x comma y and x comma y comma z. Well, here we can probably, so any prime ideal containing yz must correspond to a prime ideal in kx. In kx is a PID, so it can only have 0 or maximal ideals. So any chain from here to a maximal ideal will have length at most 1. This and the maximal ideal, as opposed to this, there is at one at least 2. So we should probably avoid this and we should pick one from there. Okay, so that's what we are saying here. Okay, so let's avoid y comma z. So we can pick x2. We can pick x1 to we have to avoid x. So we could pick something in the other prime. So we could pick, for example, y. And then if you add that, we will get y comma xz. Okay, then we ask for its minimal primes. So this is considered as a quotient ring of R. And if you ask ideal of a quotient ring, it would give the ideal for which it was quotient by. So it just showed up, it just said what that ideal is, which is just this ideal, y comma xz, minimal primes over that. Okay, so now we see that we can't pick any monomial, because every monomial in R must be in these two ideals. Right? If it's divisible by x, it will be inside here. If it is not divisible by x, it has to be divisible by y or z. I mean a monomial different from 1. Therefore, it must be inside here. Okay. So we can't choose a monomial as x2. So okay, these are, every monomial is in this ideal. So we could try x plus z. Then we ask R mod ideal mingens I plus the ideal generated by y and x plus z, and that gives y, x plus z, and then z square. It rearranges some term. And this we can see, leading term of this is y, leading term of this is x, and this is a monomial, so it is its own leading term. So x, y and z are leading term, x, y and the power of z are leading terms, and this is finite length. So we have picked a system of parameters y and x plus z. Okay, so this third example we will discuss after we prove the theorem. And so let's state the theorem. This is Krull, Rm noetherian, M finitely generated, then then S of M, which is the length of a system of parameters on M, is equal to delta of M, which is a degree of Hilbert-Samuel polynomial Pim for any M primary ideal I, equals the Krull dimension of M. Okay, and what is dim M? Dim M is the dimension, this is the definition of R mod the annihilator of M. Okay, so this is, we have said what dimension of quotient rings are, chain of primes in that quotient ring. Okay, so this is the theorem. Okay, just a few, just a remark, just to warm up for the proof. See, in the examples that in Macaulay that we saw, we said we had to take an element when we are constructing a system of parameter. We have to take an element that avoids primes that determine dimension, so that each time you go modulo the beginning of a system of parameters, an appropriate choice will also ensure that dimension goes down. Okay. hopefully, I mean, one can use this to prove the theorem, except there's one catch that we could use this probably to prove by induction on dimension, except one catch, which is that we don't know yet whether dimension is finite. It's only after we prove the theorem, or the first part of the proof of the theorem, that we will know that. Only then we can induct on dimension. Okay, but that is, we will need to use it. Okay, so that's one. Okay. So the idea of going modulo the beginning of a system of parameters progressively has the effect of cutting down dimension. The only point is that we have to ensure that dimension comes down to 0 when we are stuck, when we cannot find any more system of parameters. That's okay. So that we will need to prove. I mean, we'll need to prove an equivalent statement. Okay, so now let's prove the theorem. Okay, so we will prove 3 statements, which is one which we have already proved. We will prove that dimension of M is less than or equal to the degree of the Hilbert-Samuel polynomial, of a Hilbert-Samuel polynomial, but the degree is independent, less than or equal to. Okay, we already proved that this is less than or equal to Sm. This we already proved. Okay, and then finally we will prove that Sm is less than or equal to dim. Okay, so the 3 inequalities, if we prove, we'll finish. Okay, so we will prove these things. We'll prove these 2. This already done. Okay, so let's prove this. Let's prove this and this. Okay, so we know that this is a finite number, okay, because it's a degree of a polynomial. We know that Sm is a finite number because maximal ideal is finitely generated, and definitely system of parameters cannot have length greater than or equal to a generating set of maximal ideal. So these 2 quantities are finite, delta and S. This will ensure that dim is also finite, and then we will be able to do induction using dim. Okay, so this is induct on delta. Okay, what does that mean? Okay, so if when would delta of M be 0? Okay. Delta of M is 0 means that this, okay, so this function n going to, maybe, okay, so delta of n 0 means that, this implies that the function which takes n to the length of M mod in M is eventually constant okay, that this just because a polynomial has degree 0. Okay, so this is, and eventually meaning for all n larger than or equal to 0, much larger than 0. It's constant, but that would imply that I to the n plus 1 m is equal to I to the n m for all n sufficiently large. Okay, but this is just I times I to the n plus 1 m, I times I n m. Okay, so this is inside the maximal ideal. Some proper ideal this is finitely generated. So this is inside the maximal ideal. This is finitely generated. Therefore, by Nakayama lemma, INM equals 0 for all sufficiently large n. Okay? In other words, I to the n is inside the annihilator of M for all sufficiently large. Okay? Or in other words, the annihilator of M is M primary, okay, and M is finitely generated. So M is Artinian, and this implies that dimension of M is 0. Okay, so the inequality is preserved, both are 0. I mean, if this is 0, then this is also 0. Okay, remember, we are trying to prove this. Okay, so if the right hand side is 0, left hand side is also 0. That's the that's the base case. Okay, so now assume that delta is now assume that delta of M is positive. Okay, if dimension of M is 0, then we are okay, then there is nothing to prove. Okay, so if it is not, okay, maybe there exists, so notice that there exists P inside minimal prime of M such that dimension of M equals dimension of R mod P. Okay, that's because dimension of a module is the dimension of M R mod, the annihilator of the module, and minimal prime over M means minimal prime at which M localized at P is non-zero. So therefore, those are exactly this. They will be minimal prime in R mod, minimal prime over the annihilator of M, and this is so we have this. Okay, but this is minimal primes are associated. Minimal primes are associated. Okay, hence there exists a P in spec R such that dimension of R mod P is dimension of M. There is a P prime ideal such that dimension of R mod P is dimension of M, and R mod P injects into M as an R module. So we proved earlier that delta of a submodule is less than or equal to of a module, okay, and dimension of this is equal to dimension of that. So if you prove the inequality for R mod P, then we are done. Okay, therefore, without loss of generality, we may assume that M equals R mod P. We will see why this is helpful. Okay, just to recap, we want to replace by some nice module. So we look at a minimal prime that determines dimension, so that on the lower side there is no change. This is, we have this equality, and on the right side there is a desirable inequality. Okay, so if you prove for this, it will also hold for M. Okay. Okay, so so now so much of the argument doesn't use that dimension of M is non-zero, so this is okay. So assume dimension of M is positive. Okay, if it is 0, there is nothing to prove. Okay, since dimension of M, which is dimension of R mod P, is positive, there exists some X inside M but not in P, the maximal ideal, such that there exists some M in P. Okay. X is a non-zero divisor on R mod P. Okay. Because if X kills some Y bar inside this ring, then X times Y is inside P, but then X is not inside P, so Y must be inside P. Okay. So therefore Y bar is 0. It's a non-zero divisor on this. So now we have 0 to R mod P to R mod P multiplication by X to R mod P plus X to 0. Okay. So this is, we saw that delta of a quotient by a non-zero divisor is strictly less than delta of M. Okay. Okay. So now, so this much we have. We would like to argue that, sorry, we will be a little bit careful about choosing this x, which okay. So this is true for every p. So let me just make an emphasis of this, that actually this is true for not there exist, but for all x in M, but not in P. Okay, so just an observation. So I mean, we have to use an induction hypothesis. Okay? This is how we will use it. Now we will choose x carefully to get the desirable inequality in dimension. Okay, so let P contained in P1, contained in P2, PL, this is inside M, be any chain of primes. Okay. If we show that L is less than delta of M, then the supremum of all such L will also be less than or equal to delta of M. Okay. So it's enough to show that L is less than or equal to delta of R mod P. Okay, because the dimension of R mod P is the supremum of all such L. If for any chain the length is less than or equal to delta of R mod P, then it would imply that for the dimension also. It's supremum also. Okay, so so now choose x inside P1 but not inside P. So this is the choice that we needed. Okay. This implies that L minus 1. Okay, so now look at R mod P plus x. Okay. P1 PL is a chain containing P plus x, chain of primes. Okay. Therefore, by induction, L minus 1, which is the length of this, so this is, remember this is length is equal to L minus 1. Okay. It starts from P1 to PL, so there are only L minus 1 jumps. Okay. So L minus 1 is less than or which is L minus 1, which is less than or equal to dimension of R mod P plus x. Okay. This is strictly this is less than or equal to d delta of R mod P plus x, which is less than delta of R. Okay, so this is why we can use induction. Remember, so this is the why we can use induction. Okay, so we are working for a module with a smaller delta. So for that, dimension is less than or equal to delta, and this L minus 1 is less than or equal to dimension. So now, therefore, L is less than delta, but then we have to worry about supremum of such L, and L is less than or equal to delta. Once you add 1 on both sides throughout, one would lose, which is okay. So this implies that L is less than or equal to delta of R mod P, delta of R mod P. Okay, delta of R mod P. So this is true for every L, therefore supremum also is true. This is true for the length of every chain of primes, so therefore dimension of R mod P is less than or equal to delta of R mod P. And we have already observed that if you prove for primes like this, then we have also proved for all modules. Okay, so this proves one of the inequalities. So let's just briefly go back and see what was so what was the strategy? The strategy was to prove that dimension is less than delta, delta is less than s, which has already been established, and now we need to establish this, which we will do in the next lecture.